Okay, this is how your diagram should look like. There's something missing on my graph, however, and that's the normal. The two normals. Okay. There you go. Now, something you need to really take care of is that this angle should equal this angle. Okay. Obviously the angle of refraction, the angle of incidence, this one, needs to equal angle of reflection, this one. These two need to equal each other. This is the law of reflection. Also, something I really want you to take care of is that you don't need to waste your time drawing other rays, checking the angles. I will show you a trick to draw this 100% correct. Okay, I'm just getting an empty page. Let me show you. Alright, if you have an object here, you want to draw its image, and this is the mirror, right? The image will always be the same distance from the mirror, but on the other side. So if this is 1 centimeter, then you get your ruler, measure the distance. If this is 1 centimeter, then distance from here to the image is also 1 centimeter. Okay, so right now I just measured with my ruler and I located my image. Will I just take the 4 marks? Of course not. We're not going to take 4 marks. So here is what we're going to do. After we located the image, as shown, you're going to cheat a little bit. Now, how did we find this image? Obviously using the back extensions. Okay, so you draw back extensions, make them hit the mirror like this. Now these extensions are basically the reflections, right? So we continue straight line like this. Now these reflections are as a result of this incident ray coming from the object, right? Okay, let me do it in a different color. Connect them like this. All you need to do next is just draw the arrows. Okay, just draw the arrows and draw the normal. Now, is this accurate 100%? Yes, this is accurate 100%. You'll get the 4 marks and everything. Will this angle be equal to this angle when Mr. Examiner checks? Yes, this angle will be equal to this angle. So this is a pretty easy way to find the location of an image from an object. And this is what I did over here. It's a bit challenging, however, to draw on this iPad, so I didn't really record it. Okay, let's move on. Electricity. So figure 8.1 is a circuit diagram. Calculate the resistance of the circuit. Now, as we can see, these 2 resistors are actually series to each other. So we can calculate their total resistance by basically just adding them together, and this will give me 12 ohms. Okay, now these 12 ohms are actually parallel to this 6 ohm resistor. So to calculate the total resistance in a parallel circuit, we have this formula that is product over sum. Okay, product as in 12 times by 6 over 12 plus 6. And this gives me 72 over 18, which is 4. This is 4 ohms. There is also another way which you can do it. You know, the usual 1 over R1 plus 1 over R2 brackets -1, but I don't really prefer this method. I don't like it. Okay, so this one is easier. However, if you're given more, for instance, if you're given here a 4 ohm resistor parallel to another 6 ohm resistor parallel to a 2 ohm resistor, if you're given more than 2 resistors or 2 components parallel, then you should definitely use the other method. Okay, but it never came, and I don't think it's in the O-level syllabus. Okay, so now it asks me the potential difference across the 8 ohm resistor. It wants the potential difference across the 8 ohm resistor. So let's clear this up. This is a parallel circuit, so this one receives 24 volts. And these two, if we put a voltmeter here, these two will receive 24 volts together, right? Okay, but which one will receive more? The one with the higher resistance, of course. Now we can do this the ratio way, where this one gains double this one, and this is the easiest way. Or you can find the total current, and then the total current will be divided among these two. It's harder. And then these two will receive the same current, so you can calculate the voltage from the current using Ohm's law. I'm gonna use the ratio method. Okay, so these two will receive 24 volts. Okay, so for the 8 ohm resistor, for the 8 ohm resistor, it will receive 24 times 8 over 12 times 8. It will receive 16 volts. This is the ratio method. If I say that 12 ohms get 24 volts, then how much does an 8 ohm resistor get? Same thing, it's 8 times 24 divided 12. Same thing, 8 times 24 divided 12 gives me 16 volts. It's just the working out. Okay, that's good. State the names of the circuit components A, B, and C. A is just a resistor, plain old resistor. Component B is a thermistor. This one is the temperature one. As the temperature increases, its resistance decreases. And the component C is LED, or you can say a light emitting diode. Next, the circuit can be used to indicate a change in temperature. State and explain what will be observed when the temperature changes from hot to cold. This is what was I explaining with the thermistor. Okay, so when the temperature decreases, here the temperature decreases, so it gets colder. Let's do it in another color. So the temperature decreases, the voltage increases. When the voltage increases, the LED will glow more brightly. Okay, so LED, this is a really important question. Okay, so LED will light brighter as the temperature decreases. Resistance of thermistor increases, and becomes high, so voltage across thermistor increases. The voltage across the thermistor increases. Now this is not like the usual, okay? Let's see what happens when the voltage across the thermistor increases. So the current is flowing, passes through the resistor, flows. Now here we have a junction. Will it go this way or that way? The resistance across here is really high. Current loves to flow in low resistance, so it goes this way. So there will be current flowing through LED. Now these 3 points, this one, these 3 points are memorized, okay? But not a lot of people point out this one, okay? This question is cancelled. This is logic gates. Okay, this question. It asks, it says, figure 10.1 shows a wire that carries a current into the page. The circles on figure 10.1 show the pattern of the magnetic field. Draw an arrow in each circle to show the direction of the magnetic field. Now this is done by the right hand grip rule. Okay. And obviously I cannot really show how to do it. I can represent, so imagine this is your thumb, okay? It goes into the page, okay? So put your thumb on the table, close your fist, put your thumb on the table, and the direction in which your 4 other fingers point to, that's the direction of the magnetic field. Okay, and it's really important to use your right hand. So when I did it, the arrows were going clockwise, this direction. Okay, and using the right hand is really important. Okay, so they go this direction. It says state why. Wait, let's me draw these arrows better. Okay. State why the spacing of the circles increase as the distance from the wires increase, as the magnetic field is getting weaker. Good. Next. Figure 10.2 shows an electric door lock. The slot in the door contains an unmagnetized iron bolt attached to a spring. The slot in the door frame is empty. The slot is surrounded by coils of a solenoid. In figure 10.2, the door is unlocked. The spring is not stretched. In figure 10.3, the door is locked. The spring is now stretched. All this is nonsense so far. The bolt is initially in the position shown in figure 10.2. Describe and explain what happens when switch S is closed. Okay, now I'm getting through the stuff. So if you close this, the current will flow, okay, and it will flow through the solenoid. And because the current is flowing here, it will magnetize this bar. When this bar is magnetized, it will magnetize this bar. And when both are magnetized, they attract each other. Okay, this is basically what we're going to say. So let's say when switch S closes. Current flows through the solenoid. This magnetizes the the solenoid becomes magnetized. Oops. So bolt becomes magnetized. With opposite poles. With opposite pole. Both attract. The bolt is attracted and the door locks. Spring stretches. Because he tells us that the spring stretched. What happens when the switch S is reopened? The solenoid demagnetizes. And bolt returns back to original position. Original position. Nice. Last question, last page. The radioactive isotope bismuth 210 decays by B particle emission, beta, to an isotope of polonium. Complete the nuclide equation that represents this decay. First of all, this one is known. 0 minus 1. Okay, now a really important notice is that the mass number goes on top and the atomic number goes on the bottom. I always remember it by Z and A. Atomic number A goes down and it's not alphabetically ordered. It's from Z to A, not in chronological. Okay. So when we do 210 minus 0, it gives us 210. When we do 83 minus 1, that gives us 84. Minus gives us positive. So basically what it looked like is this. Minus and minus become positive. Okay. So basically this is equal to this. A radiation detector is placed on a bench in a laboratory where there are no artificial sources of radiation. The detector is switched on. In 7 1-minute periods, the detector displays these readings. These are all background readings. Explain why in absence of any artificial source there are readings on the detector, suggest one origin. This is due to background radiation. I'll say it comes from rocks. You can say it comes from space, food. Okay. Explain why the readings obtained are not all the same, because radiation is random. Fluctuating. The half-life of bismuth 210 is 5 days. A sample of bismuth 210 is brought close to the detector, and in 1 minute the reading displayed is 487. The equipment is left in the same place for exactly 10 days. Predict the reading in a 1 minute period at the end of this time. Okay, so it does 2 half-lives, as we can see, one after 5 days and one after another 5 days. The reading displays is 487 with the background reading. So to get the background reading, as you can see, everything is fluctuating. We don't know the exact count rate. we can calculate the average, and this will be most accurate. So 24 plus 24 plus 22 plus 25 plus 25 plus 21 plus 20. They are 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. About 23. Okay, so let's say background reading. Background reading we're using 23. Okay, we need to show our working out though, so the answer is 23. So we subtract 23 from 487, which is the reading given. So will give me 464. We divide this 2 times. 1 half-life divided 2. 2, 3, 2. Another half-life divided 2. 116. Don't forget to add the background reading after that. So 116 plus 23 is 139. Also, don't forget the units. No, there's no units. It just gave me the reading plane. Okay, this is it. Thank you, and please recommend Just Another Student to your friends and family. I hope this was really beneficial to you. Thank you.